Good evening, Professor. This is my personal timetable, today's personal timetable. What I have did in previous week and what I am going to do this current week. I have in previous week I have attended research group meeting and attended biomedical physics offline class on Friday. Every Friday we have this class of Nagendra sir class, and in this today Monday, this on the 3rd of May, I have to submit two assignments of MMIC and big data. So I was preparing my assignment and both assignment, and I've also made a presentation on of both assignment in previous week, and somehow how I got time for my research. So I was also researching about my radiometer medical sensing application using different noise source. And in this current week, as of today, I have not attended this Monday meeting, and because there was no such meeting, and yes, of course, we have on Friday we have a class of biomedical physics too, and today I'm going to submit my both assignment of big data and MMIC, and today also I'm going to present my research work, what I have done in previous week, what I have researched about the previous uh, research. And also I was searching, so in this week I will be searching for more research paper and with new things also. In this research is about design of a novel infometric microwave radiometer for human body temperature measurement. And this is the flow chart of novel infometric microwave thermometer radiometer. In this flow chart starts, and it is there are six uh, uh, entity box, and first three entity box is about hardware design, and third and last three last four is about software design. And my main focus will be on the software design infometric microwave thermometer radiometer. In this in software design section, we have three sub division subtopic, like first how for that for software design, first we have a correction algorithm. If there is an error, we use correction algorithm, then we use a calibration mechanism, then after for avoiding more error, we will be using inverse algorithm, and then the predicted temperature can be measured. In this correction algorithm microwave offset, as you can see, the temperature measurement accuracy of is improved using the correction algorithm, calibration mechanism, and inverse algorithm. In this first we will be doing correction algorithm. In this input of I and Q channels are two signals with same frequency and same system phase error has been used, and there were two equations in this volt output volt I square and IQ square as a square upon 2 cos theta whole square plus a square upon 2 sine whole square, when cos plus sine equal to 1, So after calculating, the final result will be a square upon 2. So this becomes the seventh equation, and in eighth equation is the arc 10 volt q upon volt I equal to arc 10 a square upon 2 sine upon whole upon a square upon 2 cos cos 3 pi. In this sorry, a square upon 2 get cuts, and then the sine upon cos equal to 1. So after that only pi remains. So this becomes the eighth equations. In this the phase error gain in this slide correction algorithm, the phase error, gain error and offset error affect the temperature measurement accuracy. In this the microwave radiometer is connected with sine signal with frequency of 5 gigahertz with power of 0 dBm, and the second main controller STM32 controls the phase shifter to sweep the phase 90 degree step. Then 2048 group of IQ channel voltage values are collected at each phase point, and the final result are stored in specified path according to first VI 10 into I 65535 minus 5, IQ 10 into Q 655355, pi equal to sigma, as I said in fourth point also, 2048 as a group of arctan IQ upon I whole 2048. We have when we are calculating this voltage phase at each point, the phase error is the difference between the theoretical phase value and the voltage and the phase mean value as a sample data. As you can, when temperature is 30, voltage is this much, so phase will be 49.068. The phase error, the system is obtained by averaging the phase error of the sample data, and the phase shift value of the phase shifter is controlled to compensate the system phase error. After the phase compensation, the relationship between the voltage and the sampled value should be linear. The intercept in offset and error offset and slope S is the parameter of gain, error and E gain. The idle offset error E offset idle, and idle slope S idle R. E offset equal to 0, slope idle code max minus code mean, positive voltage reference minus negative voltage reference. This is the formula for finding S idle. And when the S actual, you have to find the code correction code receiver into S idle upon S actual plus E offset correction. In this experiment, the intercept of the slope parameter obtained by linear fitting method, and the gain error, offset error and connected according to error correction method. And the corrected result of I channel is shown in this 13 figure, 19 figure. This is the correction algorithm and corrected result of I channel. And second figure is about the corrected result of Q channel using the correction algorithm. As you can see in this table also, the phase error reduced to 1.4 degrees Celsius. After the correction, the temperature changes 0.1 degree Celsius. The average of voltage also changes. In other words, the correction algorithm can reduce the influence of phase error and offset error, and the gain of the output result improve the temperature measurement accuracy. By this correction algorithm, we can improve the gain error and the output of the result, and we can also improve the temperature measurement accuracy. So this is the flow chart for correction algorithm. I will explain this flow chart. First we have to start then we have to start a data collection, then the data processing. When data is processed, if it occur a phase error, when phase or error is there in data while data processing, if it results in two boolean values, either true or false. If it is a true, phase shifter will it goes to phase shifter. If it is false, it directly goes to the gain error. If it is true, it goes to phase shifter, then it goes to the gain error. Then if there is a gain error also through the output of true or false. If there is a gain error, offset error is true, linear fitting algorithm it use linear fitting algorithm. If gain error offset is false, becomes false, it directly shows and then corrected output voltage. So this slide is about design of this is second subtopic of calibration mechanism of microwave radiometer. In this, a calibration algorithm is divided into step-by-step calibration and overall calibration also. When 50 current microwave is loaded, the output is 1.328 volt. When 75 current microwave loaded, the V out is 1.204 volt. Impedance of microwave load is 50 and the physical temperature TR is 30.3 degrees Celsius. So the equivalent noise temperature T reference has a formula of T reference 1 whole T reference square upon multiply by TR. Among this, we have the impedance. T reference can also be calculated by using this formula: impedance, this TR reference upon impedance plus reference. In this, we are using this formula V out and V1 upon T reference. In this, we have the value of all the corresponding entity, and then after calculating we get the final result of 0.01. So this becomes the 30 equations. So after that, uh, we get a curve of microwave load by using y equal to mx plus c equation formula. By using that formula, you can plot this curve of micro load, and according to equation 31 and 32, we get this kind of output volt. And this table is about validation data. Data observing the material, what will be the temperature, emissivity temperature and corrected voltage. In TA, brightness temperature of observing material. In EB, AB, emissivity of observing material. TAB is a physical temperature of observing material. And in this this table is about data of aluminum barrel and observing material of overall calibration. And we have these two equation by using this table. As you can see, we had used the corrected voltage and the emissivity, and we have formed two equation, and we have to solve this two equation using simultaneous equation method, and that you get the value of A and B. A is 0.0019 and B is 1.1999. And then using that, before also I said, for plotting graph of this curve, we had a y equal to mx plus c formula. By using that formula, we are going to plot this graph. And this is the last water temperature inversion algorithm. In up to now, what I have studied in this section, I will present through this presentation. In this, for inversion algorithm, relationship to determine this relationship, brightness temperature and physical temperature has been observed, and this is certain formula, you can say, has been used for for using this uh, inversion in used in inversion algorithm. And these are the TA, what TAL stands for, and TAN stands for. I have described this in these both two lines. And in inversion algorithm, multiple linear regression algorithm and BP neural network has been used to design this inverse algorithm. So in inverse algorithm, we had used two algorithm. First is multiple regression algorithm and second is BP neural network. In multiple regression algorithm, this sample data, for example, I'm saying this, this is a sample data that for measuring this temperature, aluminum temperature, this aluminum plate temperature. This formula has been used. And then a BP neural network model. In this BP neural network algorithm, water temperature has used inverse algorithm. This is the figure of neural network model. Is Uses the steepest descent method to continuously adjust the weight and threshold of network through back propagation, and to minimize the sum of square of network error. And this process continue until the error of network output is reduced to 0.1 degree Celsius and the number of learning times is set in advance has reached. So as in this example, there are four nodes, four layers, you can say. Brightness temperature, aluminum bearer temperature, and antenna temperature, and feeder temperature had such 1 to 10 nodes, heading nodes. And output is in water temperature and error back propagation. So as I said, I have used four BP neural network used to train 125 data set around 10,000 rounds. The input variable of data set are the brightness temperature of water, aluminum plate, antenna, and feeder temperature. Output is in form of physical temperature. And the 29 group of set as data are used for verification. And this graph is about BP neural network. This is the result of when we had used a BP neural network algorithm. So this is the result of that, uh, how much we get error and actual temperature and predicted temperature. So in this prediction accuracy of the BP neural network for water temperature is below 40 degrees Celsius, higher than that of water temperature above 40 degree. The mean square error of prediction is 0.334. Thank you for this presentation. Thank you for the day.